Alright, in this part of our example problem, we're going to calculate the primary displacement where we removed the redundant reaction. Right, so we got rid of that reaction here, and now we got to go calculate that displacement due to the real loads. Now, we could do all the integration approaches and that sort of thing, but hey, there are a lot of cases already worked out for us. And so if you go to a typical beam table, the one that I provided to you has been from the Mechanics of Materials book authored by Craig, and you'll find that this simply supported beam with a uniformly distributed load is in case 5 of table E.2, right, where our location is at 20 meters from the left and our length of our situation is 35 meters. Now keep in mind, in the real beam we have a continuous two-span beam where one span is 20, one span is 15. But in this analysis that we're here now doing, we've gotten rid of that, and it's as though we have one long beam of L equal to 35. So you got to be careful of the context and how you then select the values for these parameters, right? And so our expression for this displacement anywhere along the length of the beam is given to us in this particular table. They also give us one for the slope. Note that slope, of course, is just the first derivative of this other function, right? And they give us max values, and they give us the end rotation values. The thing is, we don't want the maximum displacement. We want the displacement specifically over here at x equal to 20. So we got to be a little careful how we're going through and doing things. We're not trying to estimate or ballpark something really quick and dirty, right? We're trying to get the correct answer here, right? So I translate this expression from the table into the version that we have using the symbols that we're working with, right? So instead of a P0 in this particular table, which just stands for the distributed load, we have a W, because that's what we've been doing. That's the 20 kilonewtons per meter. Notice I've also put the minus sign in here. The table values are such that they're taking loads positive acting up, but we don't have one going up. I mean, you could have just put P0 equal to minus 20. It's the same thing as putting a minus positive 20. It's all the same thing, but you, again, got to be careful about what you're doing here and follow through in a careful way, right? So here we go. Drop in our numbers. W is the 20 kilonewtons per meter. You've got X, the location we're evaluating the displacement, is 20 meters all over the 24 EI. I'm going to keep it in terms of EI. Oh, there's another important thing. We've assumed constant EI throughout this entire beam, because when we looked at the original structure, we noted that it looks like it's the same material all the way through, and that it has the same approximate depth. Doesn't mean it's the same second moment of area, but if we're just ballparking things here, then that would be a natural assumption that it's the same beam size all the way throughout, right? Of course, when you get into real practice, you're going to either make an assumption about what you intend to do as a designer, or you'll actually have already done preliminary selection and know more details, right? Alright, so we put in all the numbers. You got to be really careful of units, right? L cubed is the 35 meters, all of that cubed, right? Minus the 2 times the L, 35 meters, times the x squared, 20 meters, all of that squared, plus the x cubed. So that's not 120 there, that's just 20 meters, all of that cubed. Now note, I did the same thing that you often are going to do, and as I'm working this out, I didn't plan ahead in the size of my fonts, and I ended up running out of space, right? So I had to sneak that down. Don't write in the margins. Keep out of there. Even this is not really all that good, right? That was a note to you, so I feel okay about that. In my real work, I may not have. Well, I really should write that down, because if somebody's doing peer review, see, that's an important thing. Somebody will do peer review. You think they want to come and verify all this stuff? Heck no! Right? But it's their job to do that, and so you tell them where you found that particular model at, and they can verify that, yeah, this is going about right. Okay? Alright, so we put all these numbers in and work through. Delta BO then equals minus 381,250. Delta BO. There's always a BO running around. Oh, sorry. Alright, so delta BO equals minus 381,000, right, 250 kilonewton meter cubed. Couple of things to take note here. and that's over EI, is that, hey guys, these are large numbers that are sitting here. When we don't work out all the last final details, these are usually pretty big numbers in the thousands, right? Tens of thousands usually for the deltas, and for the thetas, the slopes, usually maybe 1,000 ish, right? And then we're in the SI system, so it kicks it up usually another order of magnitude in terms of relative expectation of these values, right? Because that's kilonewton meter cubed. Now wait a minute, where did that come from? Well, kilonewton per meter times meter, meter divides out, and we're just left with the kilonewton. And then we got a length cubed operation going on here. Put your units in and actually look at what you've written down. Just don't assume that you've done it right, because when you put the units in, you're going to see if you actually carry it through when you've maybe made a mistake. Oops, this is a meter squared. Oh, I forgot to put the 35 millimeters in, or meters that is, in for the L. These are ways you can do the self-checking so that your peer review doesn't have to find those crazy, silly, sloppy mistakes. Alright, note a couple of really important things here. The minus sign is important. It means it's going downwards. Just talked about the scale of the numbers that we should be expecting in that calculation. But notice these units. Okay, we should expect a force length cubed in the numerator. Why is that? Again, because by the time you get done with the load part over here at the front, that becomes a force value, and you see a length cubed showing up in all this stuff over here to the right. Every single time, not even just this case of this load, you should end up in that numerator with units of force length cubed. In the denominator, you should end up with force length squared, right? That comes from the E, force over length squared. That's a pressure, really a stress, times a length to the fourth. That would be the I. So that would be force length squared, and then that over that, of course, the force goes away, L cubed over L squared becomes just length. Oh, it's a displacement. That is a translational displacement. Of course, it should be in terms of length. Right? Now, another little interesting thing here is that for a distributed load on a simply supported beam, one span, the delta max expression is 5WL to the fourth over 384 EI. If we put in our W and our L values, that would be 397.88 kilonewton meter cubed over EI, right? If we have done our work correctly up here, then of course that max value should be greater than what we ended up with. And it is. You say, oh, you got the minus sign off. Yeah, okay, whatever. You're right. You got me. Right? Minus, but no, that's not larger than that. That's technically small. Absolute value, guys. Come on. You can hang with this. Right? You guys are too smart for that. You're just having fun at my expense. Alright, so, look, this is important to do that 5WL to the fourth over 384 EI business, because this is a large number, but how do you know that you didn't just make a silly calculation mistake? I think when I performed this calculation, I had to do it 4 times before, by the time that this problem was over, before I finally figured out that somewhere else I was making a mistake, and that mistake was actually data entry into the calculator. And this little thing down here with finding out what the maximum was very helpful to decide whether or not I had made any goofy mistakes, or where actually the goofy mistake was.